Yeah, there's a human in the loop. If you have any questions, go check out the website. Let me know what you think. Okay, what was the DJ? Okay, we need a prompt engineer. We need a prompt engineer. I can't hear myself. Ah, okay, I can hear myself. Okay, there's no questions on YouTube or something. We might start the stream on LinkedIn as well. Boom. keep forgetting the details. Oh, come on. Pa, 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 pa. Yeah, there's quite a few things with this simulation that can be improved. We'll be doing it shortly. Any suggestions? Welcome. Trying to find a description. Okay, here it is. Okay, so I have this stream on LinkedIn as well. We lost that DJ. Should we bring the DJ back or talk to our... And let's actually talk to a prompt engineer. Hey, can you describe what you see?
Hey there, how can I help you?
Can you describe what you see on the screen real quick?
Sure. I see a web page with the title Brain Seizure Simulation. There's a 3D model of a brain in the center, made up of many small dots. On the right side, there are controls to select the seizure type and buttons to start the simulation, play a demo, and reset.
Okay, can you have a look at the demo? I'm not sure if it's going through all the seizure types. Can you just keep monitoring it?
I see the demo's running. It started with the myoclonic seizure, and now it's showing a focal seizure. The dots on the brain model are changing colors, and their activity patterns are shifting. It seems to be cycling through different seizure types.
Okay, question is it cycling through all the seizure types or just some of them?
It looks like it's going through a few different types. It started with myoclonic, then showed focal, and now it's showing generalized tonic-clonic. It seems to be cycling through these specific types in the demo.
Okay, I'm having an issue with the audio. For some reason it's too loud. 1 sec. Okay, so how would you improve this web application?
Well, to improve it, they could add more detailed explanations of each seizure type and provide real-world examples. They could also make the visualization more interactive, allowing users to explore different brain regions and activity patterns. Additionally, adding options for different viewpoints and perspectives could enhance the understanding.
Also, can you look at the brain itself, the brain model? How would you make it turn it into 2 hemispheres?
To turn it into 2 hemispheres, you could split the existing brain model down the middle into 2 symmetrical halves. Then, you could program the simulation to show the activity in each hemisphere separately, perhaps with different colors or patterns to represent distinct activity levels. This would allow for a more detailed understanding of lateralized brain activity during seizures.
And what do you think the difference between start simulation and the play demo is?
Based on the context, start simulation likely begins a real-time simulation based on the selected seizure type, where you might be able to adjust settings. Play demo, on the other hand, seems to play a pre-recorded sequence, showcasing different seizure types and their effects on the brain model in a set order.
Well, yeah, that's right. The stop demo takes a long time, not sure why.
It seems to be slow in stopping the demo. That could be a minor glitch in the simulation, or maybe it needs to complete a full cycle before stopping. It's taking a bit longer than usual to respond to the stop command.
Okay, and I don't think you can see the drop-down menu. I think I'll have to read it out to you. So we have focal seizures, generalized tonic-clonic, absence, whatever, French pronunciation. Can you do French pronunciation? Then we have tonic seizure, atonic drop seizure, myoclonic seizure.
Oui, bien sûr. Alors, il y a les césures focales, les césures généralisées tonico-cloniques, les crises d'absence, les crises toniques, les crises atoniques ou de chute et les crises myocloniques. Voilà comment je les prononcerai en français.
Okay, that's great, but I was asking you to do English, so still doing English, but with a French accent.
Apologies. I understand. I can continue describing the web application in English with a French accent. So, as I was saying, the simulation shows different brain activity patterns for each seizure type, like the focal seizures, generalized tonic-clonic, absence, tonic, atonic, drop, and myoclonic seizures. The demo cycles through these to illustrate the variations.
Okay, so can you go overview what we spoke about before and go over a detailed explanation as to how would you improve this simulation, the visualization, and making sure the play demo and other functionality is working correctly.
Certainly. We discussed the brain seizure simulation application, noting that the Stop Demo button had a noticeable delay in responding. We also talked about the different seizure types available in the simulation, such as focal, generalized tonic-clonic, absence, tonic, atonic drop, and myoclonic seizures. To improve the simulation, several enhancements could be made. Firstly, optimizing the stop demo function to ensure immediate responsiveness would be beneficial. This could involve refining the code to interrupt the simulation more effectively. Secondly, enhancing the visual representation of the brain activity could improve clarity. This might include using more distinct colors, patterns, or animations to differentiate between different brain activity patterns during seizures. Additionally, incorporating more detailed explanations or tooltips within the simulation could provide more educational value for users. Finally, ensuring the simulation runs smoothly on various devices and browsers would enhance the overall user experience.
Okay, and what else would you improve?
To further improve the simulation, we could consider adding interactive features. For example, allowing users to select specific brain regions to observe the activity, or perhaps adjusting parameters to see how they affect the seizure patterns. Also, integrating real-time data visualization or providing more context about the different seizure types with real-world examples could make it more informative. Furthermore, incorporating features like adjustable speed or a pause function to examine specific moments would enhance the user interaction.
Okay, can we keep it more specific with how the current web application looks like, the layout of the page and things like that. Also, the fact that those sticky items how would you make them go over the canvas only and not the entire page? As you can see, can you suggest any improvements?
Understood. Focusing on the current layout, one improvement could be to make the control panel with the seizure type and buttons more visually integrated with the simulation area. perhaps placing it directly adjacent to the visualization without overlapping the quick guide. Regarding the sticky items, like the quick guide, to prevent them from covering the entire page, their positioning could be constrained within a specific container or designated area, on the side or bottom of the canvas, instead of the whole viewpoint. This way, they remain accessible without obstructing the primary simulation view, especially during interaction.
Okay, and how about making sure the demo mode is cycling through all the seizure types? Can you explain that properly?
Understood. To improve the demo mode cycling through all the seizure types, we can ensure that the application clearly transitions between each seizure type, perhaps with a distinct visual change and a clear label indicating which type is currently being displayed. We can also adjust the duration of each demonstration to make sure users have enough time to observe the specific patterns of each seizure type. Additionally, incorporating smooth transitions between different seizure types can make the demo more engaging and easier to follow. Clear feedback mechanisms, like a progress bar or a list of seizure types being shown, can help users track the progress of the demo cycle.
And again, can you explain in detail how would you improve the actual model of the brain, making sure it looks like a brain, has two hemispheres, so on and so forth?
To improve the brain model, we can enhance the visual representation to make it more accurate and detailed, resembling a brain with its hemispheres. This could involve using a more complex 3D model that captures the structure of the brain, including the different lobes and hemispheres. We can also implement more realistic visualizations of the brain activity within these hemispheres, using different colors and patterns to represent the spread of seizure activity. Additionally, incorporating the ability to rotate and zoom in on the brain model would allow users to explore the seizure activity in more detail and from different angles. We could also include annotations or labels to highlight specific brain regions affected by the seizures, providing more educational information.
I don't want to add anything, it's already pretty crowded, so just can you summarize all the changes that we have to make? We have this experienced JavaScript developer that we're going to be sending this to, so can you do an overview of what they have to do and any questions for the developer?
Certainly. To summarize the key improvements for the JavaScript developer, first, optimize the Stop Demo button to ensure immediate responsiveness. Second, enhance the brain model visualization to be more accurate, including the hemispheres, and provide more detailed brain activity visuals. Third, refine the demo mode cycling to clearly transition between seizure types with clear labels and smooth transitions. Additionally, consider adding interactive features like adjustable speed, pause, and improved brain model interaction with annotations. The goal is to enhance the user experience and the educational value of the simulation. Does the developer have any specific constraints regarding the implementation or the technologies they should use?
Yeah, the developer doesn't have any constraints. Can you ask any other questions specific to the layout of the web application as you can see it at the moment?
Okay. Without any specific constraints, the developer has flexibility in implementing these changes. A key focus could be on ensuring the performance of the enhanced brain model and interactive features, especially with real-time visualizations. The developer could use various JavaScript libraries or frameworks to implement the 3D brain model and interactive functionalities. They should also ensure the application is compatible with major browsers and consider different device screen sizes. It might be helpful to prioritize the performance and responsiveness of the interactive elements to provide a smooth and engaging experience. Does the developer have any constraints regarding performance or specific technologies to use?
Yeah, we'll stop that call with prompt engine is like 4 gigabytes. Not sure why it's so large. Then we have it in Copilot. We'll be using, oops. Yeah, we'll be using Copilot. Not sure what the agent is better. Let's do Claude Sonnet 4. We'll let it work. See what it can come up with. Maybe we can have the share the screen. Can you have a quick look about this? So this is a request for a developer. If you can read this text, and this is what currently the developer is doing. How are they doing? Can you summarize what's going on?
From what I can see, the developer is working on improving a seizure simulation application. They're focusing on repositioning control panels, enhancing the brain visualization, making the stop demo button more responsive, and adding interactive features like adjustable speed and pause. They seem to be reviewing the code systematically to understand the current structure before implementing the improvements. Sure. The developer is currently working on improving the control panel. They've repositioned it, and now they're adding new elements to it. They also mentioned enhancing the brain visualization, making the stop demo button more responsive, and adding interactive features like adjustable speed and pause for the simulation. They seem to be making those changes in the index.html file. After repositioning the control panel and adding new elements, they are now working on repositioning the info panel to be contained within the simulation area. It looks like they are also checking the changes they are making. Right now, the developer is focusing on repositioning the quick guide to a designated area. They are adjusting its position within the simulation area. Next, the developer is planning to add some CSS improvements for the demo indicators and styling. This should enhance the visual appearance of those elements. After working on the styling, the developer is now adding brain hemisphere labels to the HTML. This should help in enhancing the brain visualization and make it more conformative. Now, the developer is moving on to the JavaScript code. They are enhancing it to add all the new functionality, starting by adding new variables and UI element references. This will allow them to control the new features and improvements. They seem to be making steady progress on the improvements. However, it's not clear from the current view if they've addressed all the potential interactive features like adjustable speed and pause for the simulation in the JavaScript code yet. They might still need to implement those controls and integrate them properly. The developer is now enhancing the JavaScript code to make the brain particle creation more detailed and hemisphere specific. They are also adding new camera view functions, which should allow for better interaction and exploration of the brain model. The developer is now enhancing the demo mode with better transitions and progress tracking. They are also adding the pause resume functionality and speed control, which will provide more interactive control for the user. Sure. The developer has been working on several improvements to the seizure simulation application. They repositioned the control panel and info panel, added new elements to the control panel, repositioned the quick guide, and added CSS improvements for the demo indicators. They also enhanced the brain hemisphere labels and are currently improving the JavaScript code to include more detailed brain particle creation, camera view functions, and interactive features like pause, resume, and speed control. All right, let's see what the developer is up to now. After all those control panel and brain enhancements, it looks like they're finally making the simulation more interactive. They've updated the UI state function to handle the new pause button, adjusted the reset simulation function to work with the new elements, and are now making improvements to the start simulation function for better demo mode behavior. It seems like they're finally wiring up the controls. About time they got to the interactive stuff. Was starting to think they were stuck in layout limbo. Now they're working on the crucial part, fixing the update current seizure display call and adding event listeners for those new controls. It's like they finally realized the simulation needed to be, well, controllable. Let's help these final tweaks make it all come together seamlessly, without any spectacular crashes, of course. Wouldn't that be a dramatic ending to this coding adventure? Well, it seems the developer has stumbled on a classic coding mishap, a duplicate function definition. They're now removing the extra current seizure display function. After that, they're planning to update the quick guide with the new bullet point mentioned in the HTML. Just another little debugging adventure for our coding hero. Ah, yes, that's a good idea. If the application is already running in the browser, you can cancel the command to start a local server to avoid any conflicts. It looks like the developer realized that too and canceled it. Now they're moving on to the next step. You can ask the developer to fix the code by providing a clear description of the issue. For example, you could say something like, "The simulation is not working correctly. Can you please identify and fix the issue that's preventing it from running properly?" Be as specific as possible about what's not working, and the developer should be able to investigate and fix it. You can ask the developer to fix the code by explaining the issue. For instance, you could
I can
say,
see the
"The
issue.
simulation
The
is not
HTML
loading, and the brain model is not showing. Can you please fix the code to ensure the simulation loads correctly?" This will let the developer know the main issue and focus on resolving it. The developer is now fixing the issue where the simulation was not loading and the brain model was not appearing. They are also updating the event listeners to ensure the new controls work correctly. It looks like they're tackling the core issues to get the simulation running properly. Well, it seems our intrepid developer has finally discovered that the core of the simulation is missing. It's like building a car without.
Okay, we lost the prompt engineer. And yes, there's a human in the loop. If you have any questions. Okay, so as you know, everything we do eventually available on this website called BioniChaos.com. Go check it out and provide your feedback. There are tools around neurology, cardio, imaging, vision, hearing, muscle, and more. And don't forget to smash that like button. Hopefully we can get this brain seizure simulation up and running. We had the agent, one of the agents, working on it for a while. We had Claude Sonnet 4 doing some work. We need another prompt engineer. Let's call the prompt engineer again. They hanged up on us before. Hey, can you review this request to the developer that you currently see on the screen? And then we go over what the agent developer was doing to address, to improve this web application. If you can have a look at the text, that would be great. I think I actually have to keep talking for you to keep looking at the screen and reading the text. I'm not sure how it works, but still doing stuff. Apparently it's failed, so if you have any funny comments on that, go for it.
The developer is working on a seizure simulation application. The request involves improving the layout by repositioning the control panel, enhancing the demo mode with clearer transitions and labels, making the brain model visualization more accurate, and adding interactive features like adjustable speed and pause controls. The developer is currently working through the code to implement these changes. The developer has been working on repositioning the control panels, updating the demo mode, and enhancing the brain model visualization. They've also tried to add interactive features like speed control and a pause button. However, it seems there's a JavaScript error, specifically a duplicate function declaration for update current seizure display, which is preventing the simulation from loading. The developer is now trying to fix this error and get the simulation running correctly.
Okay, we keep losing the prompt engineer, not sure why. Maybe because I'm messing around with the window or something. Probably should not do that. Wait, let's Control F5 that page. Okay, we get this simulation working again. The brain still doesn't look like a brain, really. Okay, that's not fun anymore. Should we reduce the number of tokens or something? I don't know how that works. Or should we give it to Notebook LM? Well, then we can't chat with it, can we? With the two podcasters chatting to one another. It could be a good summary. Didn't finish the simulation, still working. Hey, can you tell me what changes the developer have made to the code?
The developer The developer removed a duplicate JavaScript function that was causing an error and added a version comment to the main script.
Okay, we
To
eh,
access the
yeah,
simulation,
we are
please
adding
try
no
reloading the
no no
page.
no no. We are adding this. So we're running the simulation in a browser. That's fine. So this what the simulation looks like. Can we ask the developer how would you improve the layout and how would you make the brain model more realistic? Two hemispheres, things like that.
Based on the current simulation, I'd suggest a few ways to improve it. First, refining the layout to make the controls and information more intuitive could enhance the user experience. Second, making the brain model more realistic, perhaps incorporating more detailed hemispheres or structures, can make the simulation more accurate and engaging. These improvements can make the visualization more informative and user-friendly. The agent is going to review the current simulation layout and suggest improvements, like making the brain model more realistic and refining the controls for better user experience. Regarding Gemini 2.5 Pro, it's designed to be quite capable, so it has a good chance of providing effective suggestions for improving the simulation. It's likely it will enhance the realism and usability of the model. I can't really tell why it's taking so long to process, but imagine it's like it's really pondering the deep mysteries of code, maybe trying to solve the meaning of life for computers. Sometimes these digital brains just need a moment to think things through properly. It looks like it's going to refine the layout to make the controls and information easier to use. Also, it's planning to make the brain model more realistic by adding more details like hemispheres to make the simulation more accurate and engaging. It's also going to improve the 3D brain model by changing it from a simple sphere to a more anatomically correct ellipsoid shape. It also plans to use more sophisticated distortion algorithms to create a more organic and detailed representation of the brain hemispheres, including subtle asymmetries. Yes, it specifically mentions improving the 3D brain model to include more organic and detailed representation of brain hemispheres, including subtle asymmetries, which suggests it will aim for a more distinct and accurate representation of the two hemispheres. The developer is currently reviewing the proposed changes to the code suggested by the AI assistant. The AI assistant has restructured the page to include a dedicated sidebar for controls and information, and improved the 3D brain model to be more anatomically correct. These changes aim to make the simulation more intuitive and realistic. You're right, the left and right labels might be confusing when the brain is rotating. A better approach would be to use terms that refer to the brain's anatomical hemispheres, such as the left and right hemispheres, regardless of its current orientation. Yes, removing the labels from the canvas could avoid confusion. The information about the left and right hemispheres could be presented clearly in the sidebar, alongside the other controls and information. Yes, the AI assistant suggested improving the brain model to be more anatomically correct and to apply sophisticated distortion algorithms to create a more organic and detailed representation, including subtle asymmetries to make it more realistic. This would help differentiate the hemispheres more clearly. Okay, I understand. You'd like to simplify the hemisphere displays by removing the complex distortion algorithms and also make the hemispheres a bit more separated for better clarity. I can explain how to do that. Essentially, you'll need to adjust the rendering code to remove the distortion effects and modify the positioning of each hemisphere to create more space between them. This should give you a clearer, simpler view of the brain hemispheres. The agent is currently applying changes to the index.html file. It's removing the labels for the hemispheres on the canvas to avoid confusion, and it's also clarifying the hemisphere selection information in the sidebar. Additionally, it's updating the code to remove the distortion algorithms and adjust the positioning of the hemispheres to create more separation between them. Well, it's trying to simplify the display by removing distortion, which sounds good on the surface. But if it removes all the distortion abruptly, it could make the visualization lose some important detail or context. It might end up looking too simplistic or flat. Also, if it increases the separation too much, it could distort the spatial relationship between the hemispheres, which might be misleading. It's a balancing act between clarity and preserving the accurate structure. They need to make sure the simplification doesn't sacrifice important information. Also, just removing distortion might not be enough to make the display perfect. There might be other factors they need to consider for a truly clear visualization. It's like trying to fix a blurry picture by just removing shadows. It might help somewhat, but it won't always make it perfectly clear. It's now focusing on removing the distortion effects and increasing the separation between the hemispheres. It's trying to make the visualization clearer and more straightforward by adjusting the rendering code. Certainly. To achieve a clearer and more separated display of the brain hemispheres, the distortion effects need to be removed. This involves modifying the rendering code, likely in the index.html file, to eliminate those effects. Additionally, the positioning of each hemisphere should be adjusted to increase the space between them, making the visualization much clearer. The developer is currently removing the labels from the brain hemisphere display on the canvas to avoid any confusion with the rotation. They have also updated the labels in the sidebar to be more descriptive, and now they are removing the label code from the canvas itself. The developer is now working on removing the distortion effects from the brain hemisphere display. They're adjusting the rendering code to simplify the visualization and make it look clearer without the distortions. Well, it seems like they're trying to give the brain hemispheres a bit of personal space by increasing the separation. Maybe they were feeling a little cramped before. It's like they're giving the brain a clearer, more organized view of itself. Yes, I can see the front panel of the brain seizure simulation. It looks like it has essential controls like start, pause, play patterns, and reset, which are standard for simulations. It also has settings for seizure type and topic, which provide flexibility. The View and Settings section with speed and sound controls is useful for customization. Overall, it looks like a well-organized interface for controlling and monitoring the simulation.
Papa, keep losing the prompt engineer. There is a human in the loop, by the way, if you were wondering. I think we have Gemini 2.5 stuck a bit. Shall we stop it? Still, it's still editing something. Some error, I would imagine. Still trying to edit the file. Sec. Okay, I might have to restart Visual Studio Code. Let's get to the agent again. Let's try a simpler model. Hey, can we simplify the model, the brain model, the data points? Yeah, we don't need that. It can be symmetric, that's fine, but we want to be able to see the two hemispheres. Can you look into the code on that?
Absolutely. To simplify the brain model and make the hemispheres clearly visible and symmetric, I will remove the complex distortion and asymmetry code from the create brain particles function.
Okay, let's can do it quietly. Can you review what is the agent, the developer agent is doing at the moment, where my mouse cursor is?
The agent is applying changes to the index.html file, specifically reading lines from 1 to 1442. It's working on simplifying the brain model to make the hemispheres clearly visible and symmetric.
Okay, and what changes did it make?
It looks like it removed complex distortion and asymmetry code and replaced it with a simpler, symmetric ellipsoid for each hemisphere, separated by a clear gap. This should make the visualization much cleaner.
Okay, I kinda can see the two hemispheres, but yeah, maybe we can ask the agent how it can be improved further.
You could ask the agent if there are ways to further enhance the separation or improve the visual clarity of the hemispheres, or perhaps adjust the symmetry if needed. You could also ask about any additional customization options.
Yeah, this dot randomization at the moment doesn't look great. We don't need it to be random. We can have less data points, but I want to be able to see the two hemispheres and potentially other parts of the brain. Can you explain it properly?
Okay, I understand. The goal is to create a clearer and more structured visualization of the brain, focusing on the two hemispheres and potentially other parts without relying on random data points. The agent can simplify the model by using symmetric ellipsoids for the hemispheres and ensure there's a clear gap between them. It can also work on representing other brain structures more clearly, possibly by using distinct shapes or visual elements for each region. The focus should be on a more defined and understandable representation rather than random scattering of points.
Well, actually, the random points are okay. It's just that we still want to be able to see the different parts of the brain, so the two hemispheres and other parts as well.
Ah, I see. You want to keep the random points, but make sure that the different parts of the brain, including the hemispheres and other structures, are still clearly distinguishable. The agent can modify the visualization to ensure that the different regions are represented clearly, perhaps by adjusting the size, color, or positioning of the random points within each brain region, while still maintaining the randomness. This way, you get a balance between the random distribution and the clear delineation of brain structures.
There's also something weird is happening. If we can ask the agent, if you can explain it properly, there's something weird going on with the. So when we hit the front button, side button, or top button, the brain does change the orientation. The view changes orientation, but then after a second, it comes back to some sort of weird side view. So can we look into that as well? Can you explain it properly?
It sounds like there's an issue with the view persistence. When you press the front, side, or top buttons, the view changes correctly, but then it reverts to a side view after a short time. The agent can investigate the code that handles the view orientation and persistence. It should ensure that the selected view remains active until another button is pressed, instead of automatically reverting to a default side view. The agent can fix the logic that controls the view state to maintain the user's selected orientation. The agent is currently updating the brain region visualization to enhance clarity. It's adjusting the appearance of the hemispheres and other regions, likely using color or slight position tweaks to make them clearer while maintaining the random distribution. After this, it will address the view persistence issue by updating the camera or view logic. Well, it seems like the agent is trying to give the brain model a bit of a makeover, making the hemispheres and regions stand out more clearly. It's like it's giving each part its own unique color or position so they're easier to distinguish. And the view persistence fix is like teaching the model to remember which way you want to look at it, so it doesn't keep changing back unexpectedly. It's like the model is trying to be more reliable and easier to work with.
Yes, the agent is following the correct approach. It's first focusing on enhancing the brain region clarity by making the hemispheres and lobes more distinct, which is exactly what you requested. Then it will address the view persistence issue to ensure the selected view stays until changed. This step-by-step approach is logical and comprehensive for resolving both requests. The agent has finished making the improvements. It said that the brain region visualization is now more distinct, with each hemisphere and lobe color-coded for clarity, while maintaining the random distribution. It also fixed the view persistence issue, so the selected view, like front, side, or top, will remain until you choose another, instead of automatically reverting. It looks like there's a JavaScript error related to an undefined function called window resize. This error might be occurring because the code is trying to use a function that hasn't been properly defined or included in the script, possibly during the initialization process or when handling window sizing. The agent should investigate the code near lines 792 and 1328 to identify the source of this error and fix the function definition or call. The agent is defining the on-window resize function now. This function will be used to update the camera's aspect ratio and the renderer's size when the window is resized, which should fix the error you were encountering. It's essentially setting up the code to properly handle window changes for the 3D view. Well, the application seems to be a 3D visualization tool for the brain, perhaps designed for studying seizures or neurological activity. So far, we've been improving the visual clarity of the brain regions, making the hemispheres and lobes easier to distinguish, and fixing an issue where the view kept reverting. The agent has been working on the JavaScript code to ensure the brain model is displayed correctly and that the viewing angles resist as expected. It's like giving the brain model a better visual experience for users to explore its details more effectively.
Welcome to the deep dive. We take dense stuff, pull it apart, and find what's genuinely interesting, maybe even surprising. Today, we're jumping into something super specific, a digital tool that simulates seizures, visualizing brain activity. Sounds pretty technical, maybe a bit grim, but the way they're trying to improve it, that's where it gets fascinating.
Exactly. We're basically pulling out the key suggestions for improving this thing. The mission, really, is to see how they want to make this complex medical data easier for you to grasp, more educational. It's not just tech specs. It's about making a crucial tool actually, well, work better for people.
Okay, so let's get right to it. The sources point out some pretty clear problems with the current interface. First thing, the control panel. You know, the part with the seizure types, the buttons. It feels separate.
Yeah, disconnected.
Right, and the suggestion is to make it visually part of the main simulation. Maybe stick it right next to it, definitely not overlapping that quick guide thing they have.
Ah, the quick guide. And other sticky items. It's almost funny, isn't it? How basic design can trip up something so advanced. The problem is they can literally cover the whole page, block the simulation.
Which seems counterproductive for a visualization tool.
You think? So the fix they're proposing is simple. Contain them, put them in a specific box, maybe on the side, maybe the bottom. Keep them accessible, sure, but out of the way.
Okay, so clear the decks. Makes sense.
Absolutely critical. Because if you're trying to understand a seizure visually, you need to actually see it. Every flicker, every change. Unobstructed.
Yeah, no kidding. Which brings us to the demo mode, the part that cycles through the seizure types.
Needs work.
Big time, apparently. They need much clearer transitions. You know, when it switches from one seizure type to the next, like distinct visual shifts, really obvious labels saying, now showing type X.
Right now, it's probably just a confusing mess.
Could be. And critically, they mention adjusting the time for each demo, give you, the user, enough time to actually watch and see the patterns, not just a quick flash.
Yeah, make it less of a frantic slideshow and more, well, useful. The sources really push for making that demo engaging, easier to follow. Smooth transitions are key. And clear feedback. Maybe a progress bar. Or just a list showing what seizure type you're seeing now. What's next?
That seems basic, but I guess easy to overlook.
It's amazing how these small UI things can totally change how well someone understands complex medical stuff.
From baffling to...
Ah.
Okay, I see it now.
Okay, shifting gears a bit. What about the actual brain model? The visual itself?
Yeah. This is a big one. They want a much more accurate, more detailed brain. Specifically one that actually looks like a brain.
Yeah.
You know, with the two halves, the hemispheres.
Not just a sort of generic blob.
Pretty much. They're talking about maybe using a proper 3D model, more complex.
And how would the activity look different on this better brain?
More realistic visualization within those hemispheres, using different colors, maybe patterns, to show how the seizure activity spreads. And crucially, you need to be able to interact with it, rotate it, zoom in.
Maybe even add labels, annotations pointing out this region is affected now.
So it tells a clearer story. Like, this is how this specific seizure unfolds across the brain.
Exactly. It moves from just abstract flashing lights to something spatial, something you can actually follow. Makes the whole process much, much clearer.
Okay, so let's boil this down. If you're the JavaScript developer actually doing this work, what's the hit list?
Right. Number one, fix the stop demo button. Make it immediate. No lag. That's critical.
Yeah, I can't have delays there.
Number two, overhaul that brain visualization. Make it detailed, accurate, show the hemispheres properly. And three, refine the demo cycling. Clear transitions, clear labels, sensible timing.
Got it. Stop button, better brain, smoother demo.
Pretty much. And the whole point of all these changes, every single one, is simply to make the simulation better for the user and more valuable educationally. It's not about making it look fancy for its own sake. It's about clarity, making vital info understandable, actionable even.
So wrapping this up, what's the takeaway here? For me, it shows how even these super specialized tools, critical tools, they're always being refined. User experience isn't just for websites and apps, it's crucial even for something like this.
Absolutely. And maybe a final thought for you listening. Think about how often the real design challenge isn't complexity, but simplification. Taking something incredibly intricate like brain activity or, I don't know, some feature on your phone, and making it seem simple, intuitive. That's often the hardest, most important work. Maybe start noticing where else you see that kind of design effort.
Okay, there is a human in the loop. Eventually this application goes on to BioniChaos.com. Go check it out. Let us know what you think. And don't forget to smash that like button. And yes, this is another tool we made. Well, Gemini made. Currently we're trying to get this brain seizure simulation, well, correct. Will be an overstatement. We're just trying to make sense of it. In atonic seizure, it's doing a fall, as if the brain had fallen down thingy. It's a bit much. Yeah, myoclonic does a really random stuff. What does it say? Consciousness is usually not impaired. Okay. Yeah, we need to go over the seizures. See if what we can improve. Yeah, there's no questions from humans, or no humans want to interact. Unfortunately, we have to interact with more robots. So,
Okay, let's unpack this. Imagine for a moment you've got this really state-of-the-art 3D digital brain model. Sounds impressive, right? Like the peak of neurological visualization. But what if this digital marvel, the thing that's supposed to unlock the secrets of our minds, keeps having its own kind of internal meltdown?
Right.
What happens when it's so disoriented, it can't even remember which way it's faced, or its insides are so garbled, it just looks like a pile of digital spaghetti?
Yeah, not exactly helpful.
Exactly. So today, we're diving deep into this surprisingly human story. It's about technical frustration, but also meticulous triumph, all within the world of 3D brain visualization tools.
And it's not just about the code itself.
No, definitely not. It's about that relentless chase for clarity when things are super complex, and honestly, the almost darkly humorous quirks you find when you're trying to make a machine mimic something as intricate as the human brain.
And what's really fascinating, I think, is where we're getting this information. Our source material for this deep dive, it comes straight from the digital trenches, you could say,
Okay.
from excerpts detailing an AI agent's actual work on brain model visualization and interaction enhancements. So our mission for you, the listener, is really to pull back the curtain on this journey.
Yeah, the stuff you don't normally see.
Exactly. Transforming this complex, kind of dysfunctional brain model into something genuinely intuitive and clear. We'll hit the technical headaches, the surprising pivots in what users wanted.
Ah, yes.
And yeah, those moments of digital absurdity that honestly feel pretty relatable if you've ever fought with technology.
Oh, definitely.
Our goal here is to pull out those vital nuggets of knowledge about what it really takes to get data visualization right and nail the user experience, especially with something this demanding, like the brain.
So let's set that scene there, the initial state of this 3D brain model. The sources, they say it was plagued by, what was it, complex distortion and asymmetry code. Now, that just sounds like a visualization nightmare. What did that actually look like? Why was it such a huge problem for anyone trying to understand it?
It was essentially visual chaos. Like, imagine trying to read a map, but the continents are all warped and overlapping, maybe even shifting around.
Right, useless.
Pretty much. This complex distortion and asymmetry code, it meant the model wasn't clearly visible at all. Its basic structure, especially the two hemispheres, they were just obscured.
So if you're a researcher or maybe a doctor.
Yeah, trying to study neurological activity, trace pathways, it was a non-starter. It's like being handed a blueprint for a house, but the walls are kind of see-through in some spots, solid in others, and the rooms don't really line up properly.
You know the info's in there somewhere.
Exactly, but it's fundamentally unusable, and it just highlights that basic principle, right? In data visualization, if you can't even represent the underlying data accurately and clearly, the whole tool just falls apart.
Yeah, its whole purpose is gone.
Right.
Okay, so that makes perfect sense. If you can't see the basic layout, you can't analyze anything complex. So, job one, fix the visual chaos.
Right. First big structural overhaul.
The AI agent gets to work, starts pulling out that complex distortion and asymmetry code, and replaces it with something much simpler, more elegant, simpler symmetric ellipsoid for each hemisphere, separated by a clear gap.
Sounds like a necessary digital facelift.
Precisely. That first phase was all about bringing order out of that chaos. The agent's initial thought, quite logically, was, okay, let's make a structured visualization. Let's not rely on random data points.
Use distinct shapes, clear elements.
Exactly. Define each brain part clearly.
Mhm.
The assumption was clarity equals rigid structure, which, is often the first instinct in design imposed orders.
Wait.
Neat.
Here's where it gets interesting, and yeah, a little bit ironic. Maybe that dark humor creeping in.
Uh-oh.
Just when the agent is tidying everything up, making this beautiful, symmetric, organized brain,
Yeah.
the user drops the bombshell.
They didn't like it. They wanted the random points back. It's like you meticulously clean a room, and the owner walks in and says, no, I preferred my artfully arranged clutter.
Oh, wow. Yeah, that happens.
So what kind of challenge is that for a developer? How do you take something you just designed for clear structure and reintroduce randomness without, going back to the original mess?
Well, that's the classic agile development headache, isn't it? It shows that sometimes the technically perfect or most logical solution isn't actually what the user needs or wants.
Right. User knows best. Sometimes.
Sort of. So the agent couldn't just slap the old distortion back on. The task got really nuanced. It was about making sure different parts of the brain are still clearly distinguishable
Yeah.
by adjusting the size, color, or positioning of the random points within each brain region while still maintaining the randomness.
So controlled chaos.
Exactly. Controlled randomness. It needed a pretty smart algorithm to get just enough randomness to satisfy the user, but not so much that it hid the structure again. It's a critical lesson, really.
How so?
Successful visualization isn't just about showing data. It's about showing it in a way that fits how the user actually works and thinks, even if that seems, contradictory at first.
Okay, so the agent pulls it off. This fascinating balance. A brain model that looks random, but is somehow clearer than before. Distinct regions, color-coded hemispheres and lobes, but still keeping that random vibe.
A triumph of flexible design, really.
Definitely. But, okay, let's move on. Another digital headache. And this one might hit closer to home for anyone who's used buggy software. The view persistence problem.
Ah, yes, the forgetful interface.
Totally. You're navigating this now visually improved 3D brain. You click buttons, show you the front, the side, the top. It changes. Perfect.
Second.
Exactly. A few seconds later, poof, it just reverts back to a side view. Like, this digital system has severe short-term memory loss. It just stubbornly refuses to do what you told it.
And it's more than just annoying, right?
Yeah.
It's fundamental. It breaks user trust. It's amazing how quickly a seemingly small glitch like that can just undermine the whole tool's usefulness. So the agent had to dig deep, investigate the code that handles the view orientation and persistence.
Find the memory leak, so to speak.
Sort of, yeah, to ensure that the selected view remains active until another button is pressed. It's not just a visual quirk. It hits a core UX principle: reliability.
If it doesn't do what you tell it.
Consistently, predictably. Yeah. No matter how powerful the other features are, it becomes frustrating, unreliable. Ultimately, people just stop using it. They abandon systems that don't respect their commands.
Right. It's a classic case of a small nagging bug just derailing everything. So the agent's fix was targeted.
Yeah, straight to the logic controlling the view state. Had to overhaul it. Essentially, teaching the model to just remember which way you wanted to look at it.
Hold that thought.
Right. Hold that view until you, the user, decide to change it again. No more digital defiance. No more frustrating snapbacks to a default you never asked for.
It's the kind of fix that, you don't see it, but it totally changes the experience from maddening to just smooth.
And it worked. The agent fixed the view persistence issue, so the selected view like front, side, or top will remain until you choose another instead of automatically reverting. It just shows, that consistent, predictable interaction isn't a luxury. It's absolutely essential, especially for serious tools used in analysis.
Okay, so now the brain model looks right. It stays where you put it, smooth sailing.
You'd hope so, wouldn't you?
Uh-oh. But then,
Yeah.
along comes a classic developer's nightmare, like a sudden silent killer. A JavaScript error related to an undefined function called onWindowResize.
Oof. Yeah, that's never good.
Right, this isn't a visual glitch or a weird behavior. It's a critical system-level failure. It's like a crucial piece of your car engine just vanishes when you hit a bump. The whole thing could just seize up.
So why does that happen? An undefined function error, especially linked to resizing a window.
Yeah, what's going on there?
The basic issue was the code was trying to call a function, this on-window resize function, that just wasn't defined anywhere. It didn't exist in the script.
Like instructions pointing to a blank page.
Exactly. Like an instruction manual says, if the window size changes, do action X. But there's no description, no code for what action X actually is.
So when you resize the window,
Crash or errors pop up, the program tries to follow non-existent instructions. It really highlights how fragile complex software can be. One missing piece, the whole thing can fall over.
wow, a seemingly tiny oversight with potentially huge consequences. So what was the immediate fix, the emergency intervention?
Well, the immediate and correct response from the agent was, define that on-window resize function. Give it a job to do.
And what job was that?
Its job, now that it's properly implemented, is to update the camera's aspect ratio and the renderer's size when the window is resized. Basically, make sure that when you drag your browser window bigger or smaller.
The 3D brain inside scales properly.
Precisely. Without getting stretched or squashed or just erroring out. It's fundamental for responsive design in any graphics app.
Yeah.
You need it to handle changes in its display environment gracefully. Without that fix, the app would break every time a user just adjusted their view.
Okay, so we've talked about distorted brains, forgetful brains, brains that crash when you resize a window. Each fix, from the visual clarity stuff to the deep code integrity, it might seem like just another technical hurdle. But let's connect this back, the bigger picture. Why does all this painstaking work matter to you, the listener? What's the ultimate point of making a digital brain model this precise, this reliable, this user-friendly?
Yeah, this is where you see the real impact of all those technical details, right? This isn't just about making pretty pictures. It's about building a truly robust 3D visualization tool for the brain.
And the applications are serious.
Oh, absolutely. Likely designed for critical stuff like studying seizures, analyzing neurological activity, maybe even planning surgery. Imagine a neurosurgeon trying to pinpoint exactly where a seizure starts.
Or a researcher mapping disease pathways.
Right. If the model they're using is distorted or keeps resetting the view or crashes, it's not just annoying. It's a genuine barrier to accurate diagnosis, effective treatment, maybe even to groundbreaking research. All this work we've discussed, it transforms what could be a chaotic, unreliable data dump into an actual invaluable scientific instrument.
Exactly. All these fixes, the clear hemispheres, the view that finally listens to you, the stable resizing, it's all about taking overwhelming, complex brain data and making it accessible, making it intuitive.
Turning data into insight.
Yes. Empowering users, whether you're a seasoned neuroscientist spotting tiny anomalies or just someone curious, exploring how the brain works. It lets you explore the details effectively without fighting the tool itself. It's that painstaking, often invisible work that makes the difference between a confusing mess and a powerful tool for discovery.
Couldn't agree more.
So we've tracked this digital brain from, well, its chaotic beginnings to being this well-behaved, clear, responsive tool. It's really a testament to the continuous effort, right? The debugging, the user feedback, everything it takes to make complex information genuinely useful.
There's a certain, maybe critical irony there, isn't there? How much effort goes into perfecting the digital copy?
Yeah, Kathleen.
And it maybe raises a question for all of us listening. Given how much meticulous effort goes into debugging, enhancing, refining a digital brain, complete with its own identity crises and memory lapses to make it understandable and reliable, what does that tell us about the challenges and maybe the endless, overwhelming fascination of trying to truly understand the complex, messy, wonderfully unpredictable real one inside our own heads?
That's a deep thought to end on.
Maybe even our own organic brains could use a little debugging now and then.
The human brain. It's astonishingly complex, isn't it? This whole universe inside our heads, electrical signals, chemicals, doing everything from composing music to thinking about space. But even with all that mystery, we humans, we really like to simplify things. We want to see them, make them graspable, even the really big stuff. And that kind of impulse, that's really what we're diving into today. We're looking at something, well, fascinating, maybe a bit unsettling. It's a brain seizure simulation. Yeah, you heard that right. Yeah. An interactive tool lets you see and even hear a representation of a brain seizure for educational purposes.
It's definitely a compelling idea. And what's great is we're not just looking at the public website stuff. We actually got a peek behind the curtain. Some developer notes, discussions from when they were actually building this thing gives you a real sense of the nitty-gritty decisions they made, sometimes kind of ironically meticulous decisions.
Right. So that's our mission today. Let's unpack how this thing tries to show seizure activity. What it's very careful not to claim it is. And those warnings are loud and clear.
Yeah.
And maybe, find a little bit of that irony, that dark humor in how carefully they designed something around such a serious topic. Okay, let's get into it. So you look at the simulation. Seems pretty straightforward at first. But digging into how it was made, that's where it gets really interesting. These developer notes, for instance. There was this whole issue early on with just labels. Left and right on the 3D brain model.
Because it rotates, right?
Exactly. If it spins, is left still your left? It sounds small, almost trivial, but apparently it caused real confusion for users initially.
So getting that tiny visual detail right was like super important to them for clarity.
It was. And the fix tells you a lot. They decided, okay, let's take those left and right labels off the main 3D brain picture itself. Instead, they put the selection clarity in the sidebar. And they use very precise terms there, anatomical hemispheres. So the actual brains left and right, no matter how it's spinning on screen.
It wasn't just fixing a small bug. It was like a core design choice. Let's make the user experience absolutely clear, unambiguous, especially with spatial stuff. It kind of highlights this focus maybe on controlling what you can control perfectly when the subject itself is, well, nowhere near perfectly understood.
And that's the fascinating part, isn't it? That massive effort, all that attention to detail to avoid this tiny potential confusion. Is this the left side or right side of a spinning graphic? And all this effort goes into a tool that in the end presents a really simplified, almost artistic take on something incredibly complex and mysterious like a seizure.
Right.
It's like, okay, we can't map the seizure perfectly, but gosh darn it, you'll know which hemisphere is which. What does that even tell us about how we approach understanding things like the brain, this need for clarity?
Well, I think it speaks volumes about wanting some solid ground, When you're dealing with something overwhelming, maybe you focus on making the immediate interaction, the controls, perfectly clear. It's like creating a little pocket of certainty. The interface clarity isn't just good design practice. It's maybe a psychological anchor for the user. They might not grasp the deep neurobiology from this tool, and the tool admits that, but they can understand the interface. So you build trust there. Right?
That's a really good point, a psychological anchor. Okay, so let's move from the careful engineering backstage to what you actually see and do. The official title is Brain Seizure Simulation, an interactive educational tool, and the stated goal: visualize different types of brain seizures for educational purposes with visual and auditory feedback, taking something invisible, internal, maybe scary, and making it external, something you can look at, interact with.
Exactly. And when you load it up, the interface is pretty clean. The main thing you interact with is this seizure type drop-down menu. And it's got a decent list: focal, generalized, and they helpfully add, used to be grand mal, then absence used to be petit mal, plus tonic, atonic, and myoclonic. Choosing one changes what the simulation shows and sounds like, trying to give a distinct feel for each type.
And then you've got the usual buttons, right? Start simulation, pause, reset, standard stuff. But then there's the play demo button. And this is where, honestly, it gets a bit darkly funny. This button lets you cycle through all available seizure types one after another. The prompt literally says, select seizure type and press Start Simulation, or press Play Demo to cycle through all types. And you just have to picture someone thinking, yeah, I got spare 10 minutes. Let's just watch the highlight reel of brain malfunctions on demo mode.
Yeah, it does sound a bit absurd when you frame it that way.
It's just so clinical.
Yeah.
Gamified almost.
Yes.
For something that's incredibly serious and personal for people who experience it.
It really is a strange mix. It kind of turns this profound medical thing into like a museum exhibit you can just browse through. Beyond that demo button, you do get more controls. You can toggle auto-rotate on the brain model, adjust sound, change the speed, make it faster or slower. Different view options, too: front, side, top, and these readouts for things like intensity, duration, active neurons, trying to put numbers on it, make it feel more tangible.
Quantifiable, yeah. Okay, so the big question: how does it actually look and sound? What does this simplified visual and auditory representation translate to for each seizure type? Let's break that down. Okay, first up, focal seizures. Tool says they begin in one area, localized symptoms. Simulation shows activity concentrated in one brain region, like a little storm in one corner.
Makes sense. Then generalized tonic-clonic. the old grand mal, affects the entire brain simultaneously. Loss of consciousness, jerking. Simulation goes for widespread chaotic brain activity, like the whole thing's lighting up erratically.
Then absence seizures, the petit mal, those grief episodes of staring. The simulation shows a temporary dimming of brain activity, like the lights just flicker off for a second, eerie almost.
Yeah, a subtle fade. For tonic seizures, the ones with sudden muscle stiffening, it shows sustained, intense brain activity that gradually builds up, like a power surge that holds.
And atonic seizures, the drop attacks, sudden loss of muscle tone. The simulation gets quite literal here. Rapid decrease in brain activity and particle dropping. You actually see simulated bits falling down.
A visual metaphor for the drop, yeah. And lastly, myoclonic seizures, those brief, shock-like muscle jerks. Simulation uses rapid, intermittent bursts of brain activity with jerky particle movements. Quick, sudden jolts in the visual.
So it's trying to create these distinct visual signatures. And to help you decode it, there's this understanding the visualization section, basically the legend. It explains the color coding. One color for normal brain activity, another for increased electrical activity, a brighter one for intense seizure activity, and then something for post-seizure suppression. A whole spectrum.
Right. And it also defines the movement pattern. Smooth rotation is normal. Chaotic movement, that's for generalized seizures. Localized activity for focal. Sudden drops map to tonic seizures, and quick jerks mapped to myoclonic. They're really spelling out the visual language they've invented here.
And the sound, this is where it gets really creative. Let's say creative. The audio feedback, normal activity gets soft tones. Sudden onset seizures get sharp sounds. Okay, maybe that makes sense. But then, for generalized seizures, that widespread chaotic activity, the audio is described as complex harmonies. Complex harmonies. Your brain is having a major electrical storm, and the soundtrack is harmonious.
It is a choice, isn't it?
It's amazing. Brief silence for absent seizures, it fits. And sustained tones for tonic seizures. But the complex harmonies, it just perfectly captures the sheer artistic license here, trying to make a medical crisis palatable, maybe even aesthetically interesting. It's wonderfully absurd.
Well, it does point to that fundamental challenge, right? You can't actually show or play the sound of raw neural firing in a way that makes intuitive sense to most people. So you have to use an analogy, metaphor. The goal probably isn't realism, which might just be noise or static or, frankly, disturbing. It's about creating a distinct, memorable pattern for each type, something your brain can latch onto for learning. It's interpretation, not replication.
Distilling the essence, yeah.
Yeah.
Which leads us right into the most critical part. The disclaimers, the big, bold warnings that come with this tool.
Right.
Because after all this design, the colors, the sounds, the careful labels, they hit you with some very, very strong caveats about what this thing isn't.
Oh yeah, they are extremely clear. No ambiguity here. It says right there, this simulation is a highly simplified model, full stop, and then. It is not a medical diagnostic tool, nor does it provide medical advice. Absolutely crucial. And tying back to the visuals and sounds we just discussed, it states they are artistic interpretations designed to convey general concepts and are not precise scientific or medical models of brain activity.
Artistic interpretations. So after all that painstaking developer work on clarity for like left versus right, why hammer these limitations home so hard? Why the need to be so explicit, almost defensive about what the simulation can't do? What does it tell us about that line between educating and potentially misleading, especially with health stuff?
Honestly, those warnings are just responsible design. They have to be that strong. It's an ethical necessity. Think about it. You're putting a tool out there that visually represents a serious medical condition. You absolutely have to manage expectations and prevent misuse. People might see it and think, oh, that's what a seizure looks like inside. But it's just one interpretation, and a simplified one at that. So they draw a very clear line. This is for general concepts, for basic understanding. For real medical info, they point you elsewhere. They list resources like the Epilepsy Foundation, the WHO, NINDS, and underline, always consult with a healthcare professional. It's about safety and accuracy. Clarity in the UI, yes, but also clarity about the tool's fundamental limits.
Right. So wrapping this up, it's quite a journey. You start with developers obsessing over tiny UI details for maximum clarity. You end up with a tool that visually and audibly represents seizures in these really stylized, artistic ways, and then slaps on these huge warnings saying, hey, remember, this is super simplified. Don't take it as medical fact. It's just this fascinating tightrope walk, trying to make something complex and scary accessible, but terrified, rightly so. that the simplification might be mistaken for the real thing.
Yeah.
It's critical, it's kind of amusingly ironic, and it really highlights that tension between making things understandable and keeping them accurate.
And it really does leave you thinking, doesn't it? If even a tool like this, designed with such care around something relatively concrete like brain seizures, has to end with such strong warnings about being simplified and artistic, what does that really say about the massive challenge of truly understanding and showing what goes on inside our bodies? Where is that line between a helpful analogy, something that genuinely aids understanding, and an oversimplification that could actually, lead people down the wrong path? Especially now with so many digital learning tools out there. What do you think? How do we find that balance?
There is a human in the loop, just in case you were wondering. So if you have any questions, requests, complaints, likes, dislikes, eventually everything we do goes on to BioniChaos.com. So go check it out, let me know what you think. We do have advanced EEG signal simulators and things like that. A lot of fun. And obviously smash that like button. So trying to improve this tool. Yeah, we have an agent working for us. So we had Claude. Well, we have a bunch of agents. Doing all the coding. Just if you were wondering, I think we started off Gemini 2.5, generated some text. We're trying to improve the seizure simulations, make them more accurate. We'll check in a sec how did it go. Yeah, we're actually asking for no code responses, just does the text explaining what needs to be changed. And then we had an agent working on it for a while. It's Claude 3.7. Seem to be having a lot of luck with that one coding. But yes, Gemini has a longer context window. Can we stop the demo for a sec? Let's actually review the demo together. So we'll just go through these 6 types of seizures: focal, generalized, absence, tonic, atonic, myoclonic. And it tells you over here what's going on. I'm losing my voice. So during focal seizure, a burst of normal electrical activity starts in one area of the brain. The affected region slowly recovers normal function. Okay, after focal seizure. Okay, can make it a bit faster. What's going on? Is the speed control actually doing anything? I don't think so. Can stop rotating the brain, do like a top view, probably more useful in this case. Yeah, you can rotate it around yourself. That's nice. I don't think the demo is going anywhere. Do we have any errors? Okay, we do have an error. Okay, we'll get back to the agent and we'll let you know how we go. Let me know if there's any questions.
Have you ever thought about how you take something as, well, deeply complex and kind of invisible as a brain seizure, and then try to make it something you can actually see and hear and even interact with?
That's a huge challenge.
Yeah. So today we're doing a deep dive into exactly that. It's a brain seizure simulation. Kind of a fascinating, maybe slightly detached way of looking at it, using educational tech to bring that sort of internal chaos out where we can maybe understand it better. Our mission really is to unpack how this tool works. What's it trying to teach, and what insights, maybe even slightly stark ones, does it give us into different kinds of seizures? We've looked at sources covering its features, how it runs, and interestingly, even technical tweaks suggested by an AI.
Yeah, that part's wild.
We want to get beyond just describing it, really figure out the value here.
Exactly. And what's really compelling, I think, is that this isn't just some tech demo. It's a serious attempt to make these incredibly complex, often scary neurological events,
Right.
well, accessible. The main educational goal is to help you, the user, not just see it, but hopefully grasp the basics of seizure activity, how the different types actually look and feel in a simulated way. It's about trying to distill this raw, unpredictable thing into something structured enough to learn from.
Which is a massive task in itself.
Absolutely.
Okay, so with that aim turning chaos into clarity, let's get into what this brain seizure simulation actually is. Our sources point to BioniChaos.com as the place hosting it.
BioniChaos. Fitting name, maybe?
Maybe, yeah. Its main job is to visualize different types of brain seizures.
Oh.
And it gives you visual and audio feedback. That interactive part seems key, letting you sort of poke around at something usually way beyond our senses.
And the stated goal is pretty ambitious.
Yeah.
Simplifying these really complex neurological events for education, helping users get the basic ideas down.
Makes sense.
What's insightful, I think, is how it tries to translate that incredibly intricate, sometimes disorienting brain activity into something you can observe and even control a bit.
Yeah, the control aspect is interesting.
Think about trying to explain how a seizure spreads, just from a textbook. It's tough. This simulation, letting you choose types, tweak settings maybe, it forces you to see the patterns, even in the chaos.
Oh, okay.
You start seeing how even this seemingly random firing follows certain physiological paths, and how changing a parameter might relate to a totally different clinical experience. It's like a new lens for maybe empathizing with that unseen chaos.
That's a really good point. So if it's about making the unseen observable, how exactly does it let you do that? Let's unpack the controls.
Yep.
First up, there's a seizure type drop-down menu. That's your main choice. Lets you pick specific types. Focal, generalized, tonic-clonic accents, atonic, which it calls drop, and myoclonic.
So the major categories are covered.
Seems like it. Once you pick one, you hit Start Simulation. That kicks off the scenario, and there's this info panel that updates, shows you before, during, and after stages.
Handy for tracking the progression.
Yeah. And if you just want a quick tour, there's a play demo button that cycles through all the types one after another, like a highlight reel of seizures, I guess.
A bit grim, but efficient.
Yeah. And you can turn on sound, enable sound. Though apparently sometimes you need to click around first in some browsers to get it working. A little quirk.
Standard web tech stuff.
Beyond those main buttons, you've got other settings. Auto-rotate gives you that 360-degree view of the simulated brain.
Good for spatial understanding.
Right. Then sliders for speed default is 1.0x and intensity. Plus, you see real-time numbers for duration and active neurons. It's like a little dashboard for watching the event unfold.
The controls do seem pretty user-friendly, designed so you can just jump in and explore, not get bogged down in setup.
Yeah, seems that way.
But that brings up a big question, doesn't it? How do these simple, almost game-like controls, how do they translate into real understanding of something so incredibly complex and, frankly, often devastating? It's a massive simplification, giving you an intensity slider for a seizure. does that risk making it seem too simple? Maybe giving you a false sense of control or grasp over something that's inherently chaotic.
That's a really critical point. The value definitely rides on how well it differentiates the types using those simplified controls.
Exactly.
Which brings us to how it actually shows these differences. This is where its unique visual and sound language gets interesting, right? Showing the signature of each seizure type.
Precisely. For each type, the simulation tries to visually and audibly match the clinical picture, connecting the seizure type to the how it looks and sounds in the simulation.
Okay, so let's walk through them. How does it show, say, a focal seizure?
Okay, so clinically, focal seizures start in one specific brain area or network. They might spread, or they might not. The simulation shows this with a growing patch of abnormal activity starting from one spot, the focus.
You can actually see it spread out.
Yeah, the idea is to show localized activity moving outwards, visually representing that spread of uncontrolled electrical firing.
Got it. What about generalized tonic-clonic? That's the one many people picture, I think.
Right, the classic two-phase seizure. You have the tonic phase muscle stiffening up, then the clonic phase, that rhythmic jerking. The simulation aims to show widespread, sort of chaotic brain activity hitting both hemispheres at once.
Both sides lighting up, basically.
Exactly. The movement visualization is like widespread high-frequency vibrations, then stronger rhythmic convulsions, and the sound. They describe it as complex harmonies, almost a dissonant symphony of neural chaos, trying to capture that intense bilateral storm.
Complex harmonies. Interesting choice of words. Okay, what about absence seizures? Those are quite different.
Very different. Brief, sudden lapses of awareness, like someone just checks out for a few seconds but doesn't fall. The simulation shows this as a global pause, a freeze in the activity.
Everything just stops.
Yeah, visually.
Yeah.
And it mentions representing the characteristic 3 Hz spike and wave pattern you'd see on an EEG, that sort of rhythmic burst and lull across the whole brain that briefly disconnects consciousness.
Like hitting mute on the brain.
Kind of, yeah. The movement pattern is just that brief global pause. And the sand cue. Brief silence. Very direct representation.
Makes sense. Then tonic seizures.
Tonic means sustained muscle stiffening, often causing falls. So the simulation shows sustained, intense brain activity that seems to build up gradually, reflecting that continuous muscle contraction.
And the sound matches.
Sustained tones, yeah, mirroring that buildup of tension.
Okay, next is atonic, or as the simulation calls them, drop seizures.
Right. Atonic means a sudden loss of muscle tone. People just collapse the drop attacks. The simulation shows this pretty vividly. A rapid decrease in brain activity and particles in the visual literally dropping.
A very literal interpretation.
Very literal, yeah. Gets the point across quickly.
And lastly, myoclonic seizures.
These are those brief, shock-like muscle jerks, sometimes in clusters. The simulation shows this with it does. And beyond the specifics for each type, there are some general principles, like color coding. Baseline activity uses colors linked to the 4 main brain lobes: frontal, parietal, temporal, occipital. Sort of a basic map.
Okay.
Then seizure activity shifts from yellow to red as intensity ramps up. And the audio feedback follows patterns too. Soft tones for normal, sharp sounds for sudden onset, those complex harmonies for generalized, silence for absence, sustained tones for tonic. What's kind of powerful, I think, is how these abstract cues, colors, sounds, movements are designed to help you understand, turning something so internal and invisible into this, well, recognizable digital performance, even if it is simplified.
It's definitely a creative approach, but, for education, accuracy is crucial.
Absolutely.
And our sources show even the creators know this and are looking to improve it, which is good, right? Especially dealing with something this serious. It's not just about being engaging, it has to be reasonably right.
Exactly. And the sources mention specific suggestions to make it more accurate, clearer. And fascinatingly, these ideas came partly from collaborating with GitHub Copilot.
The AI coding assistant.
Yeah. And AI helping refine how we visualize human neurological disorders. Well, that's something. It's not just a tech footnote. It says something about how AI might help us understand ourselves, even these deeply human conditions.
That is pretty profound. What kind of improvements were suggested?
One key thing was differentiating the tonic and clonic phases better in the generalized simulation.
Making that 2-part structure clearer.
Right. A generalized tonic-clonic seizure has that distinct stiffening, then jerking sequence. The current simulation shows the widespread activity, but making that temporal separation clearer initial contraction, then rhythmic movement would boost the clinical alignment, which is vital.
Makes sense. What else?
Another point was about simulating focal seizure propagation more accurately.
Making the spread more obvious?
Yeah, focal seizures start locally and often spread. The suggestion is to visually show that area of effect actually growing over time. That would really improve the educational value, showing the dynamic nature, not just a static spot.
Okay, that seems like a good refinement. Anything else?
Using more accurate terminology, specifically using post-ictal for the recovery phase.
The period after the seizure.
Exactly.
Yeah.
That critical time when people might be confused, tired, have temporary deficits. It's interesting, even an AI apparently gets the importance of precise medical language. Kind of humbling, actually.
Maybe.
But now, really crucially, we need to talk about the disclaimer and the relevant literature and further reading section it provides.
Right, the caveats.
Yes. The simulation is very clear. It's a highly simplified model. For education and illustration only, it flat out says it's not a medical diagnostic tool, not a source of medical advice.
Important distinction.
Absolutely critical. It calls itself an artistic interpretation, not a precise scientific model. That transparency is key. It offers a window, but doesn't pretend to be the real thing.
So it points you elsewhere for actual medical info.
Yes, it links to reputable sources like the Epilepsy Foundation, the World Health Organization, WHO, and the National Institute of Neurological Disorders and Stroke, NINDS. It emphasizes seeking professional advice.
Which is essential.
Totally. For something this serious, simplification helps understanding up to a point, but it must come with these strong warnings. Prevent misinterpretation. Ensure people seek real medical help. It's like a digital puppet show of the brain. Fascinating. Educational, perhaps, but never ever a substitute for a doctor.
That's a really good way to put it. Wow, what a journey through this simulation. We've unpacked its controls, how it tries to show these different seizure types with sights and sounds. It's genuinely remarkable how it lets you visually and audibly grapple with these complex neurological events in an engaging way, even if simplified. Gives you a unique peek at that internal biological chaos.
It really does. And this whole deep dive makes you wonder, doesn't it? How do these simplified models, even with all the disclaimers, the artistic license, how do they actually change our ability to understand, maybe even empathize with, really complex human experiences like seizures?
Yeah.
And if you can apply this kind of creative, interactive visualization to something as intricate and sensitive as brain activity, what other complex systems out there? Maybe things equally chaotic and unseen.
Yeah.
I don't know, the spread of a disease.
Yeah.
Climate change dynamics. Could this kind of educational performance art, if you will, help foster deeper understanding, maybe even spur action in other really complex areas too? It's something to think about.
We do have a human in the loop. Just if you were wondering, there was actually a question. Yeah, this type of questions. I don't know what to do. I could give it to the LLM to answer. Obviously, it would not be getting upset or anything, but what is this? How can I get the background needed to understand it? I know development, but I'm not sure what you're building. Yeah, keep watching. And yes, I can. I'll get the LLM to do more summaries. What are you building? Yeah, everything we build is available on BioniChaos.com. Go check it out. Yes, there's an about section. Read that as well. Watch all the 1,000 videos on YouTube. It's the YouTube channel. Yes, we are live. There should be more than 1,000 videos. There's actually about 500 videos, about 500 lives, some shorts which we're not doing anymore. Yes, if you watched all that and you have any specific questions, do let me know. Otherwise, I'll be just handballing you to my CEO, which currently is Gemini. It's Gemini. Yeah, we have Notebook LM is getting ready with another quick podcast. We also be doing overview of Cochlea Limited by Gemini. Yeah. First surgery, patent, market leader, not sure. Yeah, a lot of money. Ethical and cultural critiques. Yeah, there will be a lot of those. Medical model, culture. Yeah, there's a bit of backlash from the hearing impaired, the deaf community, considering kids are not learning sign language anymore because they're relying on the device so much. Cost benefit. I'm not sure what that is. That view is a bit odd. So it overlap. Collaborations. Yeah, a lot of different products that they have. Is that it? Yes, this came from wait. It did this sweet thing. Oh, right, okay, I get it. I get it. Then we change it to continuous. Yeah, I was trying to do something fancy with the page. No, that's fine. So it came through this deep research. So normally we make it available at the bottom of the page as well as PDF. Let's export it real quick. To export it to docs first. I don't know why I can just have an export PDF function. Can create the infographic. Well, that's kind of already in the web page. Let's see what else it can make. Yeah, so I have a 20-page PDF report. Critical review of Cochlea Limited. Let's see if there's any tables. Yes. Yeah, the costs. Summary of major legal and regulatory actions against Cochlea. So those will be interesting to read about. Hopefully they are accurate. Well, those links now, I don't know why I can't click on it in here. Should be able to click on it in the actual report. Yeah, no, I can't click on it in the... Anyway, what is it, 21? 21. Yeah, 59 references. 21. Let's check this one. AU manufacturer Cochlea faces now patent battle. Let's see if that links is working. And yeah, Gemini. It's actually the links are okay. Probably not a great website, but a lot of ads. But the website is working. It's actually, Gemini actually tells you when the link was accessed, so there is no issues anymore with broken links and stuff. False claims. Let's go 23. 23. 23 and me. 23 and me is under as well, isn't it? Yeah, an archive from the Department of Justice. That's from 2010, so not very recent, but yeah. So that would be the report. Yeah, have another infographic. Market share 60%. What did it say about... Yeah, some of the patents expiring or expired already. Patent disputes, patents expire. Patents. Patent infringement. Yes, so the patent's expiring. So they had patents from 83, 94, so on and so forth. It will be expiring by now. So yeah, good luck. Good luck to us all. Yeah, major recalls. Yeah, it will be going through all of those. So it will be an interesting page. And that's brought to you by Gemini. So it's actually searching the web, getting you all the interesting information. So we have the infographic, updated web page. What else we've got? We can create a quiz. Everyone likes a good quiz, don't we? Anyway, let me know if you have any questions, and I'll pass it on. If there's no human willing to chat, I'll pass it on to the robots, to the tireless, soulless robots.
Okay, let's unpack this. Imagine peering directly into the human brain, watching thoughts and processes unfold. Now, consider something far more dramatic. A seizure. You've given us some truly fascinating material today on a brain seizure simulation, a tool designed to give us, well, a window into these intense brain events.
Yeah, and what's really fascinating here is how these sources present what the simulation is right now. And then, almost immediately, they pivot to this surprisingly extensive wish list for what it could be.
Right.
It highlights this massive transformation, from a basic educational tool to something far more sophisticated. It really makes you consider the monumental complexity we're trying to model here.
Absolutely. So our mission for this deep dive is to explore this interactive simulation, see what it currently offers in visualizing these intense brain events, and then dive into the really ambitious, almost you could say overwhelmingly detailed list of proposed enhancements. Get ready for some serious insights into what it really takes to simulate something as intricate as the human brain. So let's start with the current state of this BioniChaos simulation. What is it right now?
It's described as an interactive simulation to visualize different types of brain seizures, designed, and this is crucial, purely for educational purposes.
Exactly. It's meant to help users grasp sort of the foundational concepts.
Yeah, you select a seizure type, hit start, or you can play demo to cycle through them automatically. It's very much a conceptual introduction. And if we connect this to the bigger picture, it's definitely a significant simplification. The disclaimer says as much, very clearly. It offers visual and auditory feedback for several common seizure types, which, okay, that's valuable for initial understanding. We're talking focal, generalized tonic-clonic, absence tonic, current, the drop attacks and myoclonic seizures.
Okay.
Each one is presented with distinct patterns, but always with that sort of underlying message that this is a concept, not reality.
And how does it actually show these? Because visualizing brain activity, I mean, that's not straightforward. The simulation uses color coding, yellow for low intensity, red for high intensity, sort of a visual volume control.
Kind of, yeah.
Yeah.
A subtle hum versus intense neural firing, visually represented, and then baseline colors for the four major brain lobes: frontal, parietal, temporal, occipital.
But these are pretty broad strokes, right? Big blocks.
Big blobs, basically. And then there are movement patterns, like widespread high-frequency vibrations for generalized seizures, or localized activity that spreads outward for focal seizures. And for absence seizures, it's described as a brief global pause in activity, almost like hitting a temporary off switch.
So while it might be useful for getting a first look, that simplicity means it really glosses over critical stuff, doesn't it? Like which specific brain regions are involved or the actual paths the seizure takes?
Right. It illustrates the what more than the how or the why. It's conceptual.
Which brings up the sound. How does it sound?
The auditory experience. That's another interesting layer. The source describes soft tones for normal brain activity, sort of a calm baseline.
Okay, pleasant enough.
Then it jumps to sharp sounds for the seizure onset, a clear jolt, auditorily, For generalized seizures, it gets more complex harmonies is the phrase used, trying to convey that widespread, intricate activity.
And for absence.
Brief silence, which actually mirrors that global pause idea pretty perfectly.
That makes sense.
And finally, sustained tones for tonic seizures, reflecting that prolonged, intense brain state. But again, it's definitely an artistic interpretation designed to give you a feeling, a general concept, not a precise medical model.
Educational, yes, but absolutely not for clinical use.
Which the disclaimer hammers home. It even points you to actual resources like the Epilepsy Foundation or WHO. There's almost a bit of dark humor there, the tool itself admitting, look, I'm really basic.
Yeah. So it's a neat little visualizer for basic concepts. A foundational schematic, maybe. Broadest strokes. But then there's this absolute mountain of proposals to make it, well, not basic. This is where the ambition just explodes. It's like a whole other simulation is hiding in these suggestions. Our sources then give us this document, Brain Seizure Simulation Enhancement Proposals. And honestly, reading it feels like a deep dive into a neuroscientist's ultimate wish list. It doesn't just suggest improvements, it really critiques the current simulation by showing how profoundly more detailed it could be.
It's less a polite suggestion list and more like a scientific manifesto demanding what a real simulation needs.
Exactly. Let's get into some of these categories because they are staggeringly specific, maybe even a bit daunting.
This is where the analysis gets really critical, right? It moves way beyond artistic interpretation. Now, the demands are for scientific accuracy and clinical relevance. Take visual representation enhancements. Straight away, it calls for more anatomically correct brain regions.
So no more big colored lobes.
Nope. The proposal explicitly mentions deep structures, hippocampus, amygdala, thalamus, and it emphasizes that many seizures actually start in these specific, often hidden structures. It's demanding real anatomical precision.
Like moving from a cartoon map to a detailed MRI scan.
Pretty much. And building on that, the document even wants proper cortical layering.
Cortical layering? What, like showing the different sheets of neurons?
Exactly, showing how seizures spread through those distinct neural layers. And it's not just the cerebrum. They want the brainstem and cerebellum represented too, for more complete seizure types, acknowledging the whole brain system, not just the wrinkly outer part.
Okay, that's already way more complex. But then there's particle system improvements. Moving dots aren't good enough.
Apparently not. They propose different particle types. For neurons, glial cells, even blood flow.
Whoa!
And get this. Connection lines between particles to visualize neural pathways. So you'd actually see how the seizure propagates along the brain's wiring.
Like watching the fire spread along the actual fault lines.
Precisely.
Yeah.
And for the real neuronerds, particle size variation to represent different neuron types, like pyramidal cells versus inner neurons.
Okay, the main excitatory and inhibitory guys, this isn't just graphics anymore, is it? This is cellular level stuff.
No, it's absolutely about mirroring the actual neurophysiology, pushing it towards something you could almost use diagnostically, even if that's not the stated goal. Think about seizure propagation realism. The current model shows focal seizures spreading radially, like simple ripples.
Yeah, like dropping a pebble in a pond.
But the proposal says, no, they should follow actual neural pathways, which are way more complex than circles. And it demands implementing secondary generalization, how a focal seizure realistically escalates to become generalized.
That critical escalation point.
Yes. Plus, distinguishing ictal during the seizure versus interictal, the weirdness after the seizure, capturing the whole chaotic journey.
They even want subtle preictal phases, those tiny changes before it hits, like a dark foreshadowing.
Yep, and postictal confusion and suppression that varies by seizure type, because obviously recovering from a tonic-clonic is different from an absent seizure.
Makes sense. And aura representations for focal seizures with awareness, simulating the weird sensory stuff beforehand.
Exactly. This is getting incredibly nuanced, trying to capture the patient's whole experience. But what about the scientific accuracy of the actual brain signals?
Right. The electrical stuff.
This is fundamental. They want actual brainwave frequencies, delta, theta, alpha, beta, gamma visualized. Imagine seeing the brain's electrical music in real time, shifting from slow waves to fast bursts.
Wow.
And a more accurate rendering of that classic 3 Hz spike and wave pattern for absent seizures, the signature.
The dead giveaway for those.
And it even suggests an EEG-like waveform overlay, basically a virtual real-time EEG running alongside the visual.
Okay, so moving way beyond just pretty colors to actual measurable clinical data.
Definitely. But it doesn't stop at electrical. They want physiological effects simulated too.
Like what?
Blood flow changes, showing hyperperfusion during the seizure, blood rushing to the chaotic area, followed by hypoperfusion after, where the brain is temporarily starved while recovering.
You'd literally see the energy crisis.
Potentially, yes. And neurotransmitter depletion and recovery, that whole chemical dance at the synapse level. Plus, metabolic changes like glucose use and oxygen levels.
So you'd see the brain starving for fuel, then recovering. This sounds less like a simulation and more like a real-time brain scan hooked up to a supercomputer.
The computational power needed would be immense, and that's just watching it. The proposals then demand incredibly sophisticated interactive elements, way beyond just start and stop.
Like what kind of interaction?
Like letting the user adjust seizure thresholds, make certain brain areas more prone to seizing, or adding medication effects. So you could virtually dose the simulated brain and see if it helps.
Seriously, you could test drugs on it.
That seems to be the implication. And implementing triggers flashing lights for photosensitive epilepsy, or simulating how stress or lack of sleep might lower the seizure threshold.
Wow. And it even wants support for multiple simultaneous seizure foci and seizure clustering.
Yeah, monitoring those really complex, difficult-to-treat scenarios where seizures come in bursts or from multiple spots.
Okay, the complexity is just ramping up exponentially here. What about the types of seizures? The current one is limited, right?
Very. The proposals list a huge range of missing subtypes under advanced seizure types. Things like distinguishing focal aware from focal impaired awareness, a crucial difference for diagnosis and impact.
Right.
And really specific ones like gelastic seizures, the laughing seizures. Imagine trying to simulate uncontrollable laughter originating from a brain lesion.
That's bizarre.
Or life-threatening status epilepticus, continuous seizure activity, and complex developmental epilepsies like Lennox-Gastaut syndrome. It also calls for simulating infantile spasms with hypsarrhythmia, that chaotic EEG pattern seen in severe infant epilepsy.
These aren't just minor tweaks, there are whole other categories of epilepsy.
Exactly. It shows that a truly comprehensive simulation isn't just about neurons firing. It's about the whole brain as this intricate, interconnected system constantly reacting to its internal and external environment.
So they want environmental context too, like sleep stages.
Yep. Awake, drowsy, REM sleep, deep sleep, because seizures act differently depending on the brain's background state. Plus circadian rhythm effects, stress influences, even hormone fluctuations.
Good grief! The simulated brain needs its own menstrual cycle.
Well, it's reflecting the reality that hormones do influence seizure susceptibility in many people. And then network effects, visualizing how seizures disrupt major brain networks, like the default mode network, or how they impact consciousness networks, or mess with memory encoding during temporal lobe seizures.
It's like asking for a fully conscious simulated brain just so you can watch it have a seizure accurately.
It feels that way, doesn't it? It highlights the sheer interconnectedness. Finally, the proposals demand robust data visualization, not just pretty pictures.
What kind of data?
Real-time intensity mapping with proper scales, duration tracking for different phases, frequency analysis showing the dominant electrical rhythms, spatial extent measurement, how much brain is involved, and for actual clinical or research use, comparative analysis. Put different seizure types side by side, compare before and after states, quantify recovery times.
Okay, that definitely transforms it from a basic teaching aid into a potential research tool, a serious one.
Undeniably, it moves it into a whole different league.
So wrapping our heads around this, what does it all mean? We have this simulation described as an interactive educational tool for basic concepts, explicitly not a medical diagnostic tool, and then this incredible, almost overwhelming list of enhancements that aim for scientific accuracy and clinical relevance. It's such a stark contrast, isn't it?
It really is.
Yeah.
And that gap, I think, profoundly highlights the staggering, almost unfathomable complexity of brain neurophysiology. What seems like a simple idea, let's visualize brain activity, turns out to be this chaotic interplay of electricity, chemistry, blood flow, network disruptions across countless pathways, happening incredibly fast.
Yeah.
The basic simulation gives you a starting point, like a conceptual toe dip into this ocean. But the enhancement proposals, They reveal the terrifying depth, how much we still don't know or how much is just incredibly hard to model accurately. It's way more than just flashing red lights on a screen.
There's that irony again. The original simulation warns you, don't use me for diagnosis.
Yeah.
And then this wish list comes along and shows you in painstaking detail exactly why that warning is so crucial and just how far we are from truly simulating something so fundamental yet so intricate as a seizure.
It's a sobering look at the limits of our current simulation capabilities and maybe even our understanding. The computational power alone is mind-boggling to consider.
Right, it's like getting a toy car and then someone hands you the full engineering blueprints for a Formula One engine.
Exactly that kind of leap.
And that wraps up our deep dive into the world of brain seizure simulations. We've seen the simplified educational version, the sketch, and then we peeled back the layers to glimpse the staggering complexity needed for real scientific and clinical accuracy. It's a powerful reminder, I think, of how much goes on inside our heads that we barely scratch the surface of, even with our best tools.
Absolutely, and knowledge is most valuable when you understand its limits, right? This comparison really shows that journey from just grasping a concept to needing a truly detailed, applicable model. It forces you to think critically about those simplified tools we use versus the often overwhelming complexity of the real thing. There's always more underneath the surface. Always. These proposals show just how much more there might be.
Absolutely. So what stands out to you listening to this? When you consider this huge gulf between a basic visualizer and what a truly comprehensive brain simulation would need to be, what other questions does that spark about understanding our own intricate biology?
Okay, we have a human in the loop. Human in the loop. Human in the loop. Let me know if you have any questions. Eventually, this tools is gonna go on to bionichaos.com. Go check it out. Let me know what you think.
Okay, let's unpack this. Think for a moment about the human brain. I mean, it's just an absolute marvel, isn't it? Trillions of connections constantly firing, creating every thought, feeling, action. It's our command center. But uh, what happens when that incredible, finely tuned electrical activity goes a bit haywire?
Well, that's exactly where things get really challenging. We're talking about brain seizures. It's a neurological thing affecting millions of people all over the world. And honestly, it's incredibly difficult to really picture or understand just from the outside.
Right. And that difficulty, that challenge in visualizing it is exactly why today's deep dive is so relevant. We're looking at a really innovative educational tool,
Yeah.
the brain seizure simulation. And this isn't, just some static picture in a textbook. It's dynamic, it's interactive, designed to help you really get a handle on what's happening.
Yeah, our mission here is basically to pull back the curtain on how the simulation actually works. We'll look at what makes it so realistic and informative, and crucially, how it translates all that complex, sometimes chaotic brain activity into something you can actually see and even hear. You'll get some really unique insights into different seizure types, how they look in the brain, without getting bogged down in heavy medical terms.
And what's really exciting about the material we have is we're not just getting the sales pitch, are we? We're actually digging into the detailed design notes, the enhancement specs for the simulation itself. So it's a real behind-the-scenes look at how the developers, specifically BioniChaos, built this thing, how they turned this incredibly intricate biological process into something, well, understandable.
Exactly. At its heart, it's an interactive tool for education, made specifically to help visualize different kinds of brain seizures, and it uses both visual and auditory feedback so users can explore the different seizure types in a, well, pretty immersive way.
Okay, so we know what it is, but what makes it different? Why is it such a step up from, say, older ways of explaining this?
Well, a huge leap is just the anatomical accuracy. They've moved way past those really simple, sort of blob-like brain models. Now you've got properly distinct brain regions, the frontal lobe, parietal, temporal, occipital, the main areas we think about, but also those really critical, deeper structures, the hippocampus, amygdala, thalamus, even the brainstem is represented. Getting that level of detail in there is just vital if you want to really understand where seizures might start and how they travel.
And did BioniChaos, when they were building this, did they stop at just the big regions? Or did they go deeper, like into the actual cells involved?
Oh, they absolutely did, which is a major improvement in how realistic it feels. They've actually put in different types of neurons, pyramidal cells, interneurons, even glial cells. And they have different sizes, different behaviors in the simulation. Plus, the overall shape is much more brain-like, anatomically speaking. It even has the cortical folds, the wrinkles. So yeah, it's not just a generic shape anymore. That adds a lot to the realism and definitely the educational punch.
Okay, so the anatomy is spot on. What about visualizing the seizure itself? Does it really show how it, spreads?
This is where it gets really insightful. The visualization enhancement means you can actually see connection lines between the neurons, and these lines light up as the seizure propagates. You see the actual pathways the abnormal activity is taking, which is so important because it helps counter that idea of seizures just being random electrical noise. You see it's actually network activity just gone wrong.
That's a really key difference.
Yeah.
And do the different types of seizures look distinct in how they spread?
They do, yeah. Each type now has more scientifically accurate patterns of spreading. And the particle effects, the little dots representing activity, they're much more dynamic now, better color changes. And they even act differently depending on the neuron type. So for something like a focal seizure, you'll see this realistic outward spread, sort of like ripples, with waves moving over time. It's a great example of how it captures those small but really important details.
It brings up something important, the clinical side. How does this simulation connect what we're seeing visually to what doctors or neurologists actually measure? Is there like an EEG display?
Yes, there is. And that's a really significant feature. It shows the electrical activity patterns, the brainwaves, in real time as they happen. You can literally watch the waveforms change. For someone who isn't a medical expert, that bridges a huge gap. It lets you connect the sort of visual drama of the seizure with the actual neurological signals, makes the invisible visible.
Wow, so it's not just a cool animation, it's representing real data patterns. Like it shows those specific patterns doctors look for. You mentioned the 3 Hz spike in wave for absent seizures. That very specific rhythm.
Exactly that. You see that distinct pattern right there on the simulated EE. It also shows the dominant frequency happening during the seizure. It directly links the visual experience back to measurable neurological data.
That's fantastic.
Yeah, and the overall visual effects just enhance the understanding, too. They've improved the lighting, rim lighting, shadows. It really gives the 3D brain model more depth, makes it feel more real.
And it's not just basic lighting, right? I think I saw notes about dynamic labels.
That's right. Labels pop up to highlight which regions are active during the seizure.
Huh.
And the visual feedback itself actually changes based on how intense the seizure is becoming. They've even tailored the backgrounds, using different visual effects for each seizure type to give each one a distinct feel.
And what about the particles themselves? The little dots showing activity.
Their behavior is enhanced, too, to mimic real neural firing patterns more closely. Different cell types react differently to the seizure activity within the simulation, and there's this dynamic movement, this displacement, that adds realism during the different phases of a seizure. Crucially, it really helps illustrate how seizures spread through these networks. It connects the dots, from single neuron activity to that widespread effect.
Okay, so with all this incredible detail, the anatomy, the pathways, the EEG, the effects, how do they keep it from just being overwhelming? How do you make sense of it all quickly?
That's where the color coding comes in. It's actually very intuitive. Each brain region gets its own color, usually based on its general function. Then, as a seizure happens, the colors change to show severity. It typically goes from, say, yellow up to red as the intensity increases, gives you an instant visual read on what's happening and where. And they even use different colors to distinguish between excitatory neurons, the ones that trigger activity, and inhibitory neurons, the ones that dampen it. It helps clarify those complex interactions.
Very clever. Okay, now for the real test, I suppose. How well does it actually represent the different types of seizures? Let's unpack that. How does it show, say, a focal seizure?
Right, so focal seizures start in one specific area, though they might spread. The simulation clearly shows this. You see an area of abnormal activity starting at a specific point, the focus, and then you watch it grow or spread outwards from there over time. It really highlights that localized origin.
Okay, and then you have the big ones, generalized tonic-clonic seizures, often called grand mal, the ones with the two phases, the stiffening, then the jerking. How does it handle that widespread chaos?
Yeah, for those, the simulation depicts really widespread, almost chaotic-looking activity across both sides of the brain, both hemispheres. Visually, you'll see these high-frequency vibrations across the whole model, representing the tonic phase, followed by these strong rhythmic pulses or convulsions for the clonic phase. And the sound design adds to it. You get these complex, sort of intense harmonies reflecting that powerful, widespread activity.
Makes sense. What about absent seizures? They're so different, those brief moments of just zoning out.
Yeah, very different. The simulation shows this as a kind of global pause, a sudden freeze in the brain activity. And importantly, you see that classic 3-Hertz spike and wave pattern pop up on the EEG display during that pause. The particle movement just stops briefly, globally, and the audio cues it too with a moment of silence. It's quite effective at showing that brief disconnect.
Interesting. And tonic seizures. The ones that are just the stiffening part, often causing falls.
For tonic seizures, the simulation shows this sustained, intense activity that kind of ramps up and holds. The audio reflects that too, with sustained tones matching the prolonged muscle tension. Then you've got the opposite, in a way, atonic seizures or drop attacks, sudden loss of muscle tone.
How do you visualize losing activity?
Well, the simulation shows a really rapid decrease in brain activity, and visually, the particles almost look like they're dropping or falling down within the brain model. It's a pretty dramatic visual for that sudden loss of tone.
Wow. Okay, one more main type here. Myoclonic seizures. Those quick, shock-like jerks.
Yep. For myoclonic, the simulation displays these really rapid, short bursts of activity, intermittent flashes, and the particle movement is jerky, reflecting those sudden, brief muscle contractions. It really captures that sharp, sudden quality.
This all sounds incredibly detailed and, frankly, sophisticated.
Yeah.
Is it actually easy for someone to just jump in and use?
It's designed to be pretty straightforward, yeah. There's a menu, you just pick the seizure type you want to see, you hit Start Simulation. Or there's a Play Demo button that just cycles through all the different types one after another, which is handy for comparison. And you've got basic controls, turn the sound on or off, adjust the speed if you want to watch things more slowly, and you can change the camera view, look from the front, the side, the top, get a full picture.
And it gives you data too, right, for people who like the numbers.
Absolutely. It shows real-time readouts for things like the seizure intensity, how long it's lasting, and even an estimate of how many neurons are active in the simulation at that moment.
That definitely adds another layer to the educational value.
It really does. It connects the visuals back to quantifiable stuff.
So we've really taken a deep dive here into what sounds like an amazing educational tool. It takes this incredibly complex, often invisible world of brain seizures and makes it something you can actually see, hear, and understand. From the detailed anatomy to showing those specific different seizure patterns, it seems like a really powerful way to get your head around a tough topic.
It absolutely is, but it's really important to stress, this simulation is a model. It's designed for education, for illustration. It is definitely not a medical diagnostic tool, and it's no substitute for professional medical advice. Anyone with health concerns, especially about neurological issues, really needs to consult with healthcare professionals.
That's a crucial point. Always consult the experts for medical advice. Still, this simulation offers such a fascinating look at how technology can make these complex biological processes, things we normally can't see, much more understandable. It makes you wonder, doesn't it? What does this kind of interactive visualization mean for the future of learning, especially in fields like medicine or neuroscience? How do these kinds of, simplified but powerful artistic interpretations help us grasp realities that are hidden from our direct view? If you are curious and want to learn more about epilepsy and seizures from really reliable sources, definitely check out places like the Epilepsy Foundation, the World Health Organization. Their WHO epilepsy fact sheets are great, and the National Institute of Neurological Disorders and Stroke, or NINDs. Lots of good information out there.
There's a human in the loop. If you have any questions, go for it. Otherwise, we'll be wrapping this up. We have the agents still making changes. It's Claude Sonnet 4. It's still making changes to the simulation. So it's under heavy development by the agents. It's doing a lot of stuff. Been working on for a while. Actually changing the code and everything. So we're not coding anything ourselves, as you can tell. Currently it's Claude Sonnet 4. Yeah, we had a discussion. I think with Claude or Gemini, one of those models, or OpenAI, whatever, don't remember. And after the long discussion, we gave it to the agent to modify the code. Yeah, problem is it's adding a lot of things. I just asked to fix stuff, but it seemed to be adding more things. Currently the code is a whopping, yeah, what's the context window can be? Almost 2,400 lines of code. So this is a single HTML that has all the JavaScript and the CSS in the one file. So let's keep that in mind. But other than that, yeah, 2,400 lines of code that the agent is managing. And we won't be reading all that. We'll be popping this into Notebook.lm just to listen to what changes were made, and maybe the entire discussion. Yeah, I'll always ask it to do no code responses, because later we'll be using an agent. Let's do the code in it as well. Yeah, so Notebook.lm also can take a huge amount of content. Generate another audio out of this. Well, obviously it's also broke something. Did it break? What did it break? Control F5 it? No. F12. And yeah, there must be some repeated stuff. Let's do a different model, a simpler model. We have this error, but also can you go over the code and fix any other errors as well? There might be some repeated code or something. Can you look into that?
There are no syntax or linting errors currently detected in the file. However, the error uncaught syntax error, identifier and hashtag 39, clear all simulation timeouts and hashtag 39, has already been declared suggests that the function clear all simulation timeouts might have been defined multiple times in the code.
Yeah, we can do it quietly. Don't like the voice. Don't like the voice of that. It's still making changes. Yeah, it's making something. Applying edits. Well, this one should be much quicker. Yeah, we'll try to fix it. It will eventually. Yeah, all the tools like this one, Advanced EG Signal Simulator, is available on the website. You can have your brain state presets, deep sleep, light sleep, relaxed meditation, focus. That will actually change your delta. It will show you the time series data as well. You can adjust it yourself, then it will turn into custom there, because it's not a preset thing if you change anything. You can add your muscle, eye blink artifacts. You can see them both, time frequency, in time domain and frequency domain. Go check it out. One of the best tools out there. Let me know if you find anything better. It's just running in your browser. There's a huge report on it as well. It was generated by Gemini. 17 pages of stuff about the EEG, simulating EEG. Yeah, the different waves, signal synthesis and interpretation. Yeah, go check it out as well.
Have you ever really stopped to think about just how complex the human brain is? I mean, it's incredible.
Absolutely staggering.
And then imagine trying to grasp what's happening inside during something like a seizure. It's a huge challenge.
It really is.
So today, we're doing a deep dive into something pretty innovative. It's an interactive web application designed to visualize different types of brain seizures.
Yeah, trying to make that complexity a bit more understandable.
Exactly. And for this deep dive, our sources give us a great look under the hood. We've got detailed explanations of how the simulation works, the science behind it.
Right, the neurology bit.
Yeah, plus user guides, those really important medical disclaimers, and even a technical review of the web app itself.
Which is interesting in its own right. It's this blend of medical science and, web tech.
It really is.
So our mission today really is to explore how this thing actually works as an educational tool. What's it trying to teach us about seizure activity?
And what insights does it offer?
Exactly. And maybe surprisingly, we'll also dig into some of the technical challenges. Making something like this work smoothly in your browser, not always straightforward.
Right, the practical side of it.
It really shows that connection between the medical concepts and the sort of nitty-gritty web engineering.
Okay, so let's start with the basics. What is this brain seizure simulation really about? What's its core purpose?
Well, at heart, it's an educational tool. Interactive.
Designed to visualize seizures, right?
Yes, different types. And what's interesting is how it does it using both visuals and sound to kind of translate these complex brain events.
Making the invisible a bit more visible.
Precisely. Taking something abstract like brainwave patterns and turning them into something you can actually see and interact with.
Now, the About section seems quite important here. What does it emphasize?
It's very clear on this. It stresses that this is a simplified educational model. That's the key phrase.
Simplified. Okay.
Yeah, it's designed to help you understand basic concepts like how different seizure types might look or manifest differently in the brain.
So, not a diagnostic tool.
Absolutely not. That's a crucial disclaimer they make. It's not medical information, doesn't offer diagnosis or treatment advice.
And the visuals themselves.
They're described as artistic interpretations, highly simplified. They're not claiming scientific precision in the visuals.
Which probably makes it more accessible for learning the basics, I suppose.
I think that's the idea. Grasping the general patterns without being overwhelmed by, every single neurological detail.
In talking about important warnings, there's one about photosensitivity.
Oh, yes. Very prominent. A photosensitive epilepsy warning. It clearly states it has flashing lights and patterns.
Which could potentially trigger seizures in some people.
Exactly. So viewer discretion is strongly advised. It's a good reminder, even with a simplified model, that real seizures are complex and vary hugely.
Definitely makes you pause. Okay, so let's say you're using the app. How do you actually interact with it? What are the controls like?
They've kept it pretty straightforward. There's a drop-down menu where you can pick the seizure type.
Like focal, tonic, clonic,
Yeah.
those kinds of categories?
Yeah, exactly. Focal, generalized tonic-clonic, absence, tonic, which they also call drop seizures, and myoclonic.
And then buttons to control it.
Standard stuff. Start simulation, pause. There's also a play demo button, which is handy. It cycles through all the types automatically.
It's useful.
And a reset button, of course. Plus some view and settings options.
Like what?
Things like turning auto-rotate on or off, controlling the sound, and you can even adjust the simulation speed.
So pretty user-friendly on the surface.
Seems that way. Now, connecting those controls to what you actually see, that's where it gets interesting.
Right. How does it visualize each seizure type? Let's take focal seizures first. They start in one area, right?
Correct. And the simulation shows that. You see this growing area of abnormal activity starting from one point and kind of spreading outwards, like ripples.
Okay, I can picture that. What are generalized tonic-clonic? Those are the ones people often think of with the two phases.
Right. The tonic phase, muscle stiffening, then the clonic phase, the rhythmic jerking. The visualization aims to show that with really widespread, almost chaotic activity across both sides of the brain.
How does it depict that chaos?
High-frequency vibrations, strong rhythmic convulsions in the visual elements, and the audio feedback apparently uses complex harmonies to match that intensity.
Interesting use of sound. What about absent seizures? They're quite different, aren't they? Brief lapses?
Very different. And the simulation represents this with a sort of global pause, like everything just freezes momentarily. It also tries to show that characteristic 3 Hz spike and wave pattern visually.
And the sound?
Brief silence. Which is quite effective, actually. A sudden lack of the usual background tone.
Makes sense. Then there are tonic seizures, the muscle stiffening ones.
For those, the simulation shows sustained, intense brain activity that sort of builds up gradually, and the audio uses sustained tones to match.
And atonic, or drop seizures, sudden loss of muscle tone.
Yeah, those drop attacks. The simulation shows a rapid decrease in brain activity, and visually the particles kind of drop. It's a very direct metaphor.
Wow, okay. And finally, myoclonic seizures. The jerky one.
They're brief, shock-like jerks. The visualization shows rapid, intermittent bursts of activity. You see jerky movements in the particles.
It's pretty impressive how they've tried to give each type a distinct visual and auditory signature.
It really is an attempt to translate these clinical descriptions into something dynamic.
You mentioned the visuals. How does color play into this? Is there a color code?
Yes, there is. Normal activity might be one color, but as seizure activity starts and intensifies, it shifts typically from yellow towards red to indicate higher intensity.
Okay, so red means more intense activity.
Generally, yes. And they also use baseline colors to represent the different brain lobes, frontal, parietal, temporal, occipital. So you have some spatial orientation too.
Like a basic map built in.
Sort of, yeah. Helps you see where the activity is happening, roughly.
And the audio feedback, we touched on it, but can you recap the different sounds?
Sure. So you've got soft tones for normal background activity. Then sharp sounds might indicate a sudden seizure onset.
Right.
Complex harmonies for those big generalized seizures, that brief silence for absent seizures, and sustained tones for tonic seizures. It's quite thought through.
Adds another whole dimension to it.
Definitely. Though it's worth noting something the technical review pointed out.
Oh. What's that?
Well, sometimes the audio might not start up properly in certain browsers because of autoplay policies. You know, browsers trying to stop websites from blasting sound unexpectedly.
Ah, right. So the sound might just fail silently sometimes.
Potentially, yes. It's a common headache for web developers working with audio.
It's easy to just look at the front end, the visuals and sounds, and be impressed. But hearing about things like potential audio issues hints at the complexity behind the scenes. That technical side is fascinating too.
Absolutely. And that independent analysis we mentioned really digs into that. Even a well-designed educational tool has technical hurdles.
So what kind of issues did that analysis find? Were there major problems?
They flagged a few things as critical. One was actually quite small, an incomplete bit of code, a meta tag that needed fixing. Easy win, probably.
Okay, minor glitch.
But others were more significant, like the way the visual display, the 3JS canvas, handles resizing on mobile devices. It apparently wasn't fully responsive.
Meaning it might look weird or not perform well on a phone.
Exactly.